Thank you for the introduction. And first of all, I would like to thank the organizers for inviting me to this nice conference. And I enjoy not only mathematics, but also for wonderful foods every day. And today, I'm talking about tight fibered knots, L-space knots, which appear in twist families of knots. And then we discuss satellite L-space knots. And this is joint work with Ken Baker in University of Miami. And I start with a comparison between Seifert genus and the slice genus of knots in twist families, and which look to have no relation with the title of my talk, but as I explain later, this has a good relation. So let me begin by recording some definitions and notations. So let K be a knot in the three sphere. Then it is well known that it bounds connected orientable surface embedded in S3, which we call Seifert surface of K. And the minimal genus of Seifert surfaces is denoted G of K and called Seifert genus, or simply genus of K. And on the other hand, if we regard the three sphere as the boundary of the four ball, then K may bound connected orientable surface which is smoothly and properly embedded in four ball, not in S3, and which may have a smaller genus. And such a surface is called a slice surface. And similarly, the minimal genus of slice surfaces is called the slice genus, or sometimes it is called the four ball genus of K. And by definition, obviously, the slice genus is less than or equal to the Seifert genus of K. And we say that K is a slice knot if its slice genus is 0. Okay. Next, we explain what is the twisting operation of knots. Perhaps you may already know, but to establish the notations. So for any knot K in S3, take a trivial knot C. And since C bounds a disk, cutting K along the disk, and after one twist, glue it back again to obtain another knot, K1. And another one twist produces a K2. And if twisting in the opposite directions, we obtain K-1 and so on. And in this manner, we obtain an infinite family of knots. And we call such a family a twist family of knots. And we are interested in the behaviors of the difference between the Seifert genus of Kn and the slice genus of Kn, and the ratio of the Seifert genus of Kn to the slice genus of Kn. And in particular, we are interested in how these values behave under twisting for sufficiently large integers n. And for each twist families, there are elementary invariants, winding numbers and wrapping numbers. So winding number of K about C is the absolute value of the algebraic intersection number between the disk delta bounded by C and K, and which coincided with the linking number, absolute value of the linking number between C and K. On the other hand, if we ignore the orientations, we have a wrapping number of K about C, and which is defined to be the minimal geometric intersection number between the disk delta and K. And the definition of the wrapping number is quite simple. But in general, it is not so easy to determine the explicit number of the wrapping number. But I think almost 100% intuitive wrapping number is the real wrapping number. But it is not so easy to explicitly determine. And in the first pictures, so K runs in the same directions from the bottom to the top. So in this case, winding number equals wrapping number is 5. And in the second picture, some strings go from go top and go down, and the winding number equals 1, while the wrapping number is 5. And in the last one, winding number is 0 and wrapping number is 4. Now we take a closer look at some examples. And I assume that for non-triviality, we assume that the wrapping number is greater than 1. For otherwise, if the wrapping number is 0, then it means that C bounds the disk disjoint from K. So any twist along C does not affect the knot type of K. And similarly, if the wrapping number is 1, then it means that C is a meridian of K. So again, any twisting along C does not affect the knot type of K. So in the following, we assume the wrapping number is greater than 1. And now we take a closer look at some examples. So in the most left picture, in this case, winding number equals wrapping number equals 2. And in this case, the difference between the Seifert genus and the slice genus goes to the genus of this local knot K. And the ratio of the Seifert genus to the slice genus tends to 1 when n goes to infinity, so twisting many times. And in the middle picture, in this case, the wrapping number is 3, while the winding number is 1. And in this case, the difference between the Seifert genus and the slice genus goes to infinity. And similarly, the ratio of the Seifert genus and the slice genus goes to infinity when n goes to infinity. So in this case, Seifert genus and the slice genus behave completely different manner in these examples. And in the last picture, so white head ring together with some small local knot. In this case, the wrapping number is 0 and winding number is 0 and wrapping number is 2. Then the difference between the Seifert genus and the slice genus goes to the genus of K, and the ratio goes to the genus of K plus 1 when n goes to infinity. So in the last one, computation is due to Casson and Gordon. And in this way, so if we consider the ratio of the limit of the ratio of Seifert genus to the slice genus, it takes several values, including infinity. So perhaps it may be natural to ask the following as the limit. So the first one, does the limit of the ratio of the Seifert genus to the slice genus always exist? Here we allow the infinity. So it means that there is a possibility vibrate. And so including infinity, this limit always exists or not? This is the first question. And by definition, the Seifert genus is greater than or equal to the slice genus. So if such a limit exists, then the limit is greater than or equal to 1. So the second, we may ask that which real number greater than or equal to 1 can be realized as the limit of the ratio of the Seifert genus and the slice genus for some twist family of knots. And in particular, can it be irrational, something like a square root of 2 or something like that. And when the winding number, our linking number is 0, then we have a Seifert surface of K, which is disjoint from C. So it means that after twisting along C, this Seifert surface remains Seifert surface for the twisted knot. Thus, the Seifert surface of Kn, hence the slice genus of Kn are bounded from the above. So we may assume that the winding number is not 0, so namely positive. Then our first result answers these questions. So for any twist family Kn with non-trivial winding number, then the limit of the ratio of Seifert surface to the slice Seifert genus to the slice genus of Kn is infinity, or otherwise it must be rational number. And for the second, for any rational number greater than or equal to 1, there exists a twist family Kn for which the limit of the ratio tends to the required given rational number R. And to prove the first result, we need to describe both the Seifert genus of Kn and the slice genus of Kn for sufficiently large n. And to prove the second, actually we construct a concrete examples which satisfy the desired property. Now, we consider the behavior of the Seifert genus G of Kn for sufficiently large integers. So here is a disk D bounded by the twisting circle C and punctured by the knot K. So D is looks like a disk, but here this disk is not a disk with puncture. So namely a punctured disk. And so in this case, one outer boundary and 1, 2, 3, 4, 5 inner boundaries. And we denote their homology class by bracket of D. So bracket of D is a homology class represented by this disk. And its Thurston norm is denoted by X of bracket of D. And using Thurston norm, recently Baker and Taylor have shown the following. So there is a constant G depending upon the knot K and twisting circle C, such that twice the genus of Kn equals the 2G plus n omega times Thurston norm of D for sufficiently large integers n. So it means that the Seifert genus of Kn is controlled by the Thurston norm of this disk, punctured disk, and winding number for sufficiently large integers n. And now for slice genus, we can obtain a similar estimate on the slice genus. And actually, we prove that there exists a constant C and C prime such that twice the slice genus of Kn is bounded from the below by C plus n omega omega minus 1, and also bounded from the above by C prime plus n omega omega minus 1. So as a direct consequence of, in this case, for all positive integer n, not necessarily sufficiently large. For this theorem, just a positive integer n. And this theorem immediately implies when the winding number is less than or equal to 1. So these are 0. So the slice genus of Kn is bounded when the winding number is less than or equal to 1. Now we omit the proof of these theorems and go ahead. And now we compare the genus of Kn and the slice genus of Kn. The result is as follows. So we suppose that the winding number omega is not 0, so namely positive. Then we have the following. So if omega equals 1, then the limit of the ratio goes to infinity. Because as I mentioned, the slice genus is bounded, and the Seifert genus goes to infinity. So in this case, always infinity. The ratio tends to infinity. And if the winding number is greater than 1, then the limit of the ratio of the Seifert genus to the slice genus is explicitly written by using Thurston norm. Namely, the limit is Thurston norm of D over omega minus 1. Okay. So hence, if winding number is not 0, then the limit of the ratio is infinity when the winding number equals 1. And otherwise, it should be a rational number. So this answers, this gives a first result. Okay. So we now give a brief proof of this theorem. We assume that the winding number is greater than 1. Then for suitably large integer n, we have that twice the genus of Kn equals 2g plus n omega times Thurston norm of d for some constant g. This g depends only k original knot k and the twisting circle c. And for slice genus, we have the equation inequality twice the slice genus of Kn is bounded from the below by C plus n omega omega minus 1 and bounded by above by C prime plus n omega omega minus 1. And in the left hand side of this second inequality, this may be negative, but if we choose n further sufficiently large, then this side is also positive. So by taking the quotient, we have the inequality for the ratio, like this. And assuming omega is greater than 1, then high school mathematics tells us the limit of the ratio is bounded from the below and bounded from the above by the same value, the Thurston norm of d over omega minus 1. So this means that the ratio of the Thurston norm, the ratio of the genus of Kn to the slice genus of Kn equals the Thurston norm over omega minus 1, as I mentioned. And so, as I mentioned, these values attains any rational number greater than or equal to 1, possibly infinity. So we are interested in the very specific case. So namely, the ratio tends to 1, the smallest value. So in other words, in this case, the Seifert general G of Kn and the slice general G4 of Kn behave asymptotically same. Then in such a situation, what can we say? And actually we can answer this question. So let Kn be a twist family of knots obtained by twisting K along the unknotted component C. If either there exists constant C such that the difference between the Seifert genus of Kn and the slice genus of Kn bounded by this constant C for infinitely many integers n. Here, we don't require this inequality holds for all sufficiently large integers n. Just we require this inequality holds for infinitely many integers n. So maybe infinite integers n destroy this inequality. Or the ratio of the Seifert genus and the slice genus tends to 1 when n goes to infinity, so positive twist, or n goes to minus infinity, so minus twist. Then we have that the winding number omega is 0, or C links K coherently. So coherently meaning that the winding number of K and equals the lapping number of K. So in other words, K laps always in the same directions. Okay. So here is a proof. We give a proof assuming the previous theorems. So we assume that the winding number is not 0, so namely omega is greater than or equal to 1. And let us take S, Thurston norm minimizing surface, which is a properly embedded surface in the exterior of the link K union C with a coherently oriented boundary, and which represents the homology class D and realizing the Thurston norm. So it is a Thurston norm minimizing surface. Then for homological reasons, the boundary of S consists of omega curves in boundary of the tubular neighborhood of K, each of which represents meridian of K, and a single curve in the boundary of the tubular neighborhood of C, which represents the preferred longitude of C. So preferred means homologically trivial in the exterior. Then, using the Thurston norm minimizing surface S, the Thurston norm of D can be written as twice the genus of S plus omega minus 1. So if we can prove that genus of S is 0, then it means that S is a punctured disk. Then S caps off to a disk S hat in S3 bounded by C that K intersects coherently. So we are done. So we need to prove that the genus of S equals 0. Okay. So now, if the omega, the winding number equals 1, then the ratio goes to infinity, as I mentioned, so contradicting the assumption. Thus, we may assume that winding number is greater than 1. Then the previous theorem for the limit of the ratio of the Seifert genus to the slice genus equals the Thurston norm of D over omega minus 1. And this Thurston norm can be written as this. So we replace this by this one to obtain this one. So twice the genus of S plus omega minus 1. And it may be simplified to this. And we have assumed here that the limit of the ratio equals 1. Here is our initial assumption. So now compare the most left and most right. We see that the genus of S equals 0. So it means that this is a coherent twist family. Okay. And now, how about the coherent twist family implies something? And let Kn be a twist family of knots obtained by twisting along K, twisting K along C. And if she links K coherently, so winding number equals the wrapping number, then we have there exists constant C plus C minus such that the difference between the Seifert genus of Kn and the slice genus of Kn equals C plus minus for sufficiently large integers plus n minus n, respectively. And hence, this implies the ratio of the Seifert genus to the slice genus tends to 1 when n goes to infinity or minus infinity. And now we consider the two measures, so the difference and the ratio. And they are related as follows by using this. So if the limit of the Seifert genus to the slice genus tends to 1, then there is a constant C such that the Seifert genus is bounded from the above by the sum, the slice genus plus some constant C for all integers n. Because this assumption implies the twist family Kn is coherent or winding number is 0. And if the winding number is 0, then, as I mentioned, both Seifert genus and the slice genus are bounded from the above. So we can find such a constant C, obviously. And if the twist family is coherent, then theorem 6 implies this equality. And this equality, so if we choose C is larger than C, replace C, we obtain the required inequality from this equality. This holds for sufficiently large integers n. So, okay. So up to now, we compare Seifert genus and the slice genus of knots in twist families. And so now we explain why we are interested in such a comparison. And to do that, we recall two notions, tight fibered knots and strongly quasi-positive knots. And first we recall tight fibered knots from contact geometry. So let K be a fibered knot in the 3-sphere. Then, by definition, it gives open book decomposition, K pi, with K a binding, and a fiber surface pages, by definition. And furthermore, Thurston and Winkeln-Kemper proved that this open book decomposition gives a positive contact structure psi on the 3-sphere, S3. And furthermore, this contact structure is unique up to isotopy by Giroux's theorem. So this means that each fibered knot can be classified into tight fibered or not, depending upon the corresponding contact structure psi is tight, meaning that no over-twisted disk or not. So next notion is strongly positive knots, which was introduced by Rudolph from braid theory. So positive Seifert surface is a surface obtained by parallel disks by attaching positive bands like this. This is a positive Seifert surface. And we say that a knot K is strongly positive if it bounds a positive Seifert surface. So this is a positive surface, and the K is a boundary, and K is a strongly positive knot. And so we now explain the two classes of knots, tight fibered knots and strongly positive knots. And at the first glance, these two knots are independent and has no relations. However, Heden and Bader Ishikawa independently proved that these classes are very strongly related. So K is a strongly positive fibered knot, if and only if K is a tight fibered knot. And these class enjoy the very nice property. So recall that Osbach-Szabo introduced a knot concordance invariant tau, which satisfies the following inequality. The absolute value of the tau of K gives the bound of slice genus and hence the Seifert genus, like this. And Livingstone proves that for strongly positive knot K, the slice genus of K equals the Seifert genus. Actually, this inequality gives the tau of K is less than or equal to the slice genus and hence the Seifert genus. And this is a crucial point for strongly positive knot. The genus of K is less than or equal to the tau of K. So this string of inequality implies the slice genus of K coincides with the Seifert genus of K. So now Seifert genus and the slice genus is a encounter. Yeah. So we can apply the previous result for strongly positive knots. Yes. And as an immediate consequence is that. So let Kn be a twist family of knots. And if Kn or its mirror, Kn bar denotes the mirror of Kn, contains infinitely many strongly positive knots, then either winding number is 0 or she links K coherently. So actually, assume that Kn contains infinitely many strongly positive knots. Then, by Livingstone theorem, the difference between the Seifert genus of Kn and the slice genus of Kn equals 0 for infinitely many integers n. So our theorem 5 shows that winding number equals 0 or she links K coherently. And as I mentioned, tight fibered knots are strongly positive. So we can say the similar result for tight fibered knots. However, for tight fibered knot, sorry, I explained this condition. So in this theorem, there is a possibility omega equals 0 in the conclusions. And actually, such a case happens. So let F be a positive Seifert surface together with strongly positive knot K as its boundary. And take a trivial knot C here as a small almost meridian of the band. And for any negative twist, here we take n equals -2. Then we obtain this picture. And slightly modify this part, twisting part, fatten a little bit to obtain the third picture. And obviously, this is a quasi-positive Seifert surface. So by definition, its boundary Kn is a strongly quasi-positive knot. So actually, this situation can happen for tight fiber, strongly quasi-positive knots. And for tight fiber knot case, we assume that Kn is tight fibered for infinitely many integers n. Then C links K coherently. So in this case, we can eliminate the possibility of omega equals 0, because in my previous joint work with Ken Baker, so winding number 0 twist family contains at most 3 tight fiber knots. So in this situation, omega equals 0 cannot happen. Just C links K coherently. And furthermore, there is a constant n such that Kn is tight fibered for every integer n greater than or equal to n. And on the other hand, Kn is tight fibered for only finitely many integer n, less than n. So roughly speaking, we have 2 integers, n and n prime. And in this side, every knot is tight fibered. And in this side, no knot is tight fibered, never tight fibered. So tight fibered, and in this side, never tight fibered knot. But we take a little bit take care about this side. So for instance, we may ask, so K minus and negative side is not tight fibered. However, if we take a mirror of them, they may be tight fibered. And actually, there is a very typical example. So let Kn be a twist family of knots. And if C is a braid axis of K, then both Kn and the mirror of K minus n are tight fibered for all sufficiently large integer n. Actually, so since C is a braid axis, Kn is a closure of positive braid for sufficiently positive integers n, because full twist is the center of the braid group. So negative crossing can be cancelled. We put many twists. And similarly, and the closure of the negative braid for sufficiently negative integers n. And a closed positive braid being a sequence of priming positive hop bands onto the disk is tight fibered. So this is a typical examples. And we omit the details. We need a little bit steps. And after characterization of minimal Seifert surface of Kn in coherent twist families of knots for sufficiently large integers n in terms of Murasaki sums, and characterization of twistings which yield more than 5 torus knots, and another one, characterization of product or closure of tangles yielding braids or closed braids. And then we develop theorem 6, characterization theorem, theorem 9 to prove the following. So which we call a characterization theorem. So let Kn be a twist family of knots. And then C is a braid axis of K. If and only if Kn and the mirror of K minus n are tight fibered knots for sufficiently large integers n. So this means that the converse of the example just I mentioned is still holds. Okay. Now, okay, so we go back to the L-space knots, which appears in the title in my talk. So, okay. So let n be a rational homology 3 sphere. Then its Heard-Freyer homology, hot version Heard-Freyer homology, satisfies in following inequality. So the dimension of the Heard-Freyer homology is greater than or equal to the order of the first integral homology of M in general. And if the equality holds, then we call M an L space. So, an L space is a rational homology 3-sphere having the simplest Hegardt-Freyer homology. And as the name suggests, length spaces other than S2 cross S1, which is not a rational homology 3-sphere, and more generally, elliptic 3 manifolds are L spaces. And there are infinitely many hyperbolic L spaces. And now, what is L space knot? So we say that K is a positive L space knot. If for some positive rational number R surgery on K resulting in an L space. And if R is negative, then we call L a negative L space knot. And only trivial knot can be both positive and negative L space knots. And so if we ignore the sign of the R, we say that K is a L space knot if K admits some non-trivial surgery yielding L space knot. We don't take care about the signs. Okay. And an L space knot is a fibered knot. So due to Gigini and Juhasz. And so firstly, Gigini proved this for genus 1 case, and then Ni generalized this. And Juhasz gave alternative proof. And furthermore, Hayden proved that positive L space knots are strongly quasi-positive fibered knots and hence tight fibered knots. So we have the following Venn diagram. So strongly quasi-positive knots are fibered knots, and this is a tight fibered knot, and positive L space knot live here. So again, we can apply the previous result for the L space knots. So one direct consequence is the following. So let Kn be a twist family of knots, and if Kn is an L space knot for infinitely many integers n, then she links K coherently. So for instance, this picture is some is go up and one is go down. So this is not coherent. So in this case, Kn is an L space knot for only finitely many integers n. Okay, now we look at some interesting examples. So here is a -231 Pretzel knot. This is I think a 2-5 torus knot, I guess. And we take a trivial knot C here. And after one twist, we obtain -233 Pretzel knot. This is again a torus knot, perhaps a 3-4 torus knot. And another one twist, we have -235 Pretzel knot. This is also torus knot, 3-5 torus knot. And another one twist, we have -237 Pretzel knot, which is a famous hyperbolic knot admitting two length space surgeries due to Finch-Sherrow and Stan. And Osbach-Szabo proved that any positive twist produces L space knots. On the other hand, Riedman-Moore proved that negative side, negative twist never produce L space knots. And in this case, this twist family contains infinitely many L space knots. And actually, as I mentioned, our theorem said that she links K coherently. Actually, in this example, this is a winding number equals 2 and wrapping number equals 2. However, she is not a braid axis. Actually, if she is a braid axis, then after twisting, any knot has a braid index 2. So it means that the resulting knot is 2n torus knot, but these are not Tn torus knot. So this is not a braid axis. Okay. So in some sense, we call such a family the one-sided infinite family of L space knots, because this side infinitely many L space knots. However, other side no L space knots. So it is one-sided infinite family of L-space knots. And so since positive L-space knots are tight fibered, so our characterization theorem implies the following. So let Kn be a twist family of knots, and we suppose that Kn is an L-space knot for infinitely many positive integers n and simultaneously infinitely many negative integers n. Then C is a braid axis of K. So for instance, this is a torus knot, and we take like this C. C is a braid axis. And actually in this example, all the knots are L-space knots. Okay. And now we take a special case. Both components are trivial knots. Then, since C is trivial, twisting K along C, we obtain Kn. And in this case, K is also unknotted. So we can twist C along K to obtain the second family, Cn. And in such a family, either Kn and Cn each contain only finitely many L-space knots, or otherwise, C is a braid axis for K, and K is also a braid axis for C. And Kn is an L-space knot for all integers n, and Cn is so. And in such a situation, the first situation shows that this link K union C is exchangeably braided due to the notion of Hugh bottoms. Okay. Now we apply our result to a study of satellite L-space knot. And let us recall what is a satellite knot. So let K be a non-trivial knot in the 3-sphere, and let V be a standardly embedded solid torus in the 3-sphere with longitude lambda V. And P is a knot inside V, any knot, just inside. And we call the pair V and P a pattern. And take an orientation preserving embedding from V into S3, which sends the longitude of V to the longitude of K, preferred longitude of K. And we often call such an embedding a faithful embedding. Then the image of P by this F, denoted by P of K, is a satellite knot with a companion knot K. In this case, K is a trefoil knot, and the pattern VP here. And in this example, the resulting satellite knot is a Whitehead double of trefoil knot. So recall that so if we perform R surgery on the satellite knot, then the result pk of R can be decomposed into the union of the exterior of the companion knot K and R surgery on the solid torus along K. So this decomposition requires a gluing condition for the glued 3 manifold to be an L space. And so explain the gluing theorem due to Hanselmann, Rasmussen, and Watson. Let X be a compact 3 manifold with a single boundary torus. And L of X denotes the set of L space fillings. Then recently, Hanselmann, Rasmussen, and Watson established the following gluing theorem. So assume that M1 and M2 have incompressible boundary, and then the glued 3 manifold M1 union M2 bears the homeomorphism H is an L space, if and only if the image of the interior of the L space filling of M1 by H and together with the interior of the L space filling of M2 form entirely a rational number together with 1 over R, infinity. So using this, Jennifer Holm proved that if a satellite knot P of K is a positive L space knot, then both companion knot K and pattern knot P are positive L space knots. And So pattern knot means, so we consider the pattern is a pair of the solid torus V and a knot in P. And pattern knot means we forget the solid torus V. Just we regard P is a knot in the 3 sphere. So the pattern knot is L space knot. So, however, this theorem gives us no information on of the pattern Vp. So, namely, how the pattern knot P is embedded in the solid torus V. And actually, Baker, Moore, and Hom conjectured that if P of K is an L space knot, then P is a closed braid in V. Okay, something like the typical example of cable knot. And also, Hom proved that if a satellite knot P of K is a positive L space knot, then a Pn, so Pn is here. Recall that we have a pattern V and P here, and take a C as a core of the companion solid torus, a complementary solid torus here. And twisting along C, we obtain a twist family of knots, Pn. And she proves that Pn is a positive L space knot for all integer n greater than or equal to minus 2g plus 1. And P minus n is a negative L space knot for all sufficiently large n. So this means that Pn is a two-sided infinite family of L space knots. So this is, we encountered just we considered previously. So this is a twist, two-sided. Here is a twist infinitely many L space knot, and also this side infinitely many L space knots. So this is a two-sided infinite family of L space knots. So we apply our previous results to prove that if the satellite knot P of K is a satellite L space knot, then it is a braided satellite knot. So namely, P is a closed braid in V. So this answers a conjecture of Baker, Moore, and Hom in the positive. And furthermore, we have the following constraint for a companion knot K and a pattern knot P for a satellite knot P of K to be an L space knot. So assume that satellite knot P of K is an L space knot. Then there is a strong constraint between the genus of pattern and the companions. So the genus of the companion knot K is strictly smaller than the genus of the pattern knot, or P of K is the 2-3 cable of the trefoil knot. So in the latter case, both G of K and G of P equals 1. Okay. So finally, we study a little further. We apply our previous results to a study of the essential tangle decomposition of L space knot. So a knot K in the 3 sphere admits an essential n-string tangle decomposition if there exists a 2 sphere S which intersects K transversely in 2 endpoints, such that the punctured sphere S minus the interior of tubular neighborhood of K, this is a punctured 2n punctured sphere, is essential in the exterior. So for instance, if K admits an essential 1-string tangle decomposition, then K is a connected sum of 2 non-trivial knots, namely K is non-prime. And if K admits an essential 2-string tangle decomposition, then K has an essential convex sphere, so 2 spheres with 4 punctures. Okay. And actually, so Kulkat-Pitch proves that an L space knot has no essential 1-string tangle decomposition. So meaning that L space knot is prime. So any connected sum cannot be an L space knot. And Liedman-Moore conjectured that an L space knot admits no essential two-string tangle decomposition. So namely, L space knot admits no essential convex sphere. And furthermore, so Baker-Moore generalized this to conjecture that an L space knot admits no essential n-string tangle decomposition for all integers n. And we apply our previous results to give a partial answer, a very small partial answer. So let P of k be a satellite L space knot with a pattern Vp and a companion knot k. Then P of k has no essential n-string tangle decomposition for n is less than or equal to 3. So in particular, any satellite L space knot admits no essential convex sphere. And if the companion knot k has no essential n-string tangle decomposition for all n, then its satellite P of k has no essential n-string tangle decomposition for all n, neither. So in particular, this first assertion gives a positive answer to Liedman-Moore's conjecture for satellite knots. However, for hyperbolic knots, it is still open. Okay, a little bit earlier, but I would like to stop here. Thank you very much.